Hi, welcome back to a world where CNC was never invented, and let's look at a technique that allows you to cut radii and angled surface without the use of a rotary table, indexer, a radius cutter, or angle table. It's kind of a same approach that a CNC machine would take if they existed, but purely manually, running the machine with hand wheels. So let's look at the technique. Frankly, it's quite simple, but there are a few things to consider. So let's have a look. So this is our first example, very simple. I have a square part, this is tool steel. So you see this doesn't work only with plastics, and we want a 10mm corner radius here and a 5mm corner radius here. Normally you have a lot of options here. If you're running a CNC, you would just cut the radius while you cut the perimeter of the part with the end mill and program a radius here. You can lay it out very carefully with dividers and file the radius, or you're a little bit more on the lazy side, you walk over to a belt or a disc sander and just do it like this. Gives often a very acceptable result, especially if you check it with a radius gauge. You can set it up on a rotary table with this as the center point and cut it with radius. You can dress a grinding wheel with the radius and grind the radius, or you use a corner rounding end mill. I used to own a corner rounding end mill, but I've thrown all of them away because high-speed steel corner rounders don't work very well for what I do. Corner rounders do a decent job, but the larger the radius, the more problematic they get, because they have a very large engagement length and don't have a helix angle, so they are a very harsh cutting tool. In many cases, that doesn't fly well with my parts. So another method is to manually CNC it, or manually contour it. For that, all we need is a milling machine, preferably with a DRO, otherwise it gets a lot of math by hand. Let's say we have a mill and a DRO, and the DRO in an ideal case has a function for bolt hole circles. Or even better, an option to mill radii. Mine has both, and the radius function really makes it very easy. All you need is the center point of your radius and your arc segment. So for example, 0 and 90 degrees. So we'll define this front corner of the part here as our 0, 0, 0, and with a 5mm radius, this direction is y plus. This first coordinate here is x minus 5, because it's a 5mm radius, and y plus 5. The second center point here is, the part is 26mm wide, so it's 26 minus 10, so, well, let's start with x. 10mm radius, x minus 10, and y is plus 26 minus 10 is 16. So, that's our two center points of the radii for doing this contour. Let's go to a milling machine and set it up. Clamp the part with overhang to the side out of the vise. Use the screw jack over here to balance out the vise jaw so it doesn't, bend. And I still get a very good grip on the part. I am cutting a 10mm radius here, so I need at least 10mm here plus the cutter radius overhang out of the vise. So probably going to use a 6mm end mill, so 6, the radius is 3mm. I need at least 13mm of overhang. I went a little bit more, 16 millimeters overhang out of the vise, just to be to have some wiggle room when I hand crank it around. I'm using a edge finder to find the front right corner of the part here. I do always a double check with the edge finder when I use it. Touch off, zero out the DRO, touch again, check my DRO reading. When it's within 10 microns, I'm happy. I'm going to use the 6mm 4-flute end mill. This is, by the way, a hydraulic chuck. I think I have shown it in the past, but people have asked about it, and it's an hydraulic tool holder. It has a very precise bore, but there is a bladder around it filled with oil, and there's a set screw pressing on the bladder and compressing the bore and squeezing the end mill that you put in there. It's a 12mm diameter holder, but it comes with very, very precise reducing sleeves. So you put in the reducer sleeve and you put in an end mill. And you just tighten down the set screw here on the side of the holder. Now you get a very good grip on the tool, very good run out, and the damping properties of these tool holders are quite good. And also the pull-out strength, or the resistance against pulling the end mill out of the holder is quite good. It's not a true roughing tool holder. There are better systems for that. Side lock tool holder would be better for roughing. A mill chuck, a real mill chuck would be better. A system like PG is better for roughing probably. But this is a very good middle point for a precision chuck. And also it's very quick to change tooling compared to, for example, a shrink fit chuck. They are very expensive though. They are a nice solution if you need to change between a lot of different tool shank diameters rather often on the same part on a manual machine compared to a collet system, especially compared to ER collets. Let's see if we can take this in one bite of depth. This is like, I haven't checked the thickness of it, but I think it's like 10 millimeters. But first we need to set the DRO. On this DRO, this is an Icron. It's very easy because it has a graphical interface and it has a radius cutting function. So you hit radius, then it asks you which plane you want to cut. We're looking down onto the radius, so we're only moving in the X and Y direction. Then it asks for an X center point of the radius. That's -5. That's already put in there. Y center point is 5, +5, as we determined on the bench. The radius is 5 millimeters. Here you can set your cutter orientation, inside or outside. You can see it flip over here on the preview screen. We want to cut outside, of course. Here you can set the start angle and the end angle. If I put in 180 here, it will cut half a circle. But we only want to cut like quarter of a circle, 1 quadrant. Then it wants a step. This determines your cusping, the height of the material left when you're done cutting. So I'm setting this to 0.2 millimeters. This will get removed by filing or stoning extremely quickly. No worries there. And it also asks for a tooling diameter. So we have a 6 millimeter end mill. And that's all. One thing that I will do is I will put the radius to 5.05. I will make it slightly bigger, just so the tangent will look very nice. So we don't cut into the parent material where we don't want it. So then you hit enter. Then it says 0.1 of 41. Then you can just step through, and with each step the XY coordinates change. And all you need to do after each step is to hand crank to 0 until you reach the last point. Then you clear the workpiece with the cutter, exit twice, and then you're back in your normal interface. So let's go back, hit enter, and start cutting. Okay, I will hand crank to X and Y 0 on the DRO, which determines my starting point of the radius we're cutting. And this is also serving as an idiot check. Does this look right? Yeah, this looks like the starting point of a 5mm radius across here. Now I'm dropping the cutter to my correct depth. In this case, just all the way through the part. I'm running at 1000 RPM, which is slower than I normally would run a 6mm end mill. But since we're doing a lot of cutter engagement here, I want to prevent chatter by running it a little bit slower. Also, you could rough it out in multiple steps of depth and with a larger radius set in the DRO, and then do a final pass with the final radius. Or you could rough it out with bandsaw. Let's see. And here is our 5mm radius. Well, 5.05mm radius. And we see a little bit of cusping, faceting. But really, this is a really nice radius. In many cases, you could leave it like this without any additional handwork. And yeah, this is not the fastest technique. This is really relatively slow. But sometimes this is faster than ignoring the fact that CNC exists since 30 years for the average shop. But considering manual machines and having to set up a rotary table, or not having to set up a rotary table and just, for example, cut 1 or 2 radii on a part, well, this is a very viable option. Even if you have to cut multiple radii, and even angled surfaces are tangent to a radius, this technique is really powerful, and I will show you a little bit more later. But as I said, it's slow. But also we cut this radius on this like 10mm thick piece of tool steel in one go. Granted, the milling machine I'm using is reasonable stiff, but this would also be possible on the machine I had before. Let's just use the radius function again. Our X center point moves to -10 because we have a 10mm radius. Our Y moves to, the workpiece is 26mm wide, 10mm radius, so it's 16. The radius is 10. Let's do the 50 micron safety to get a nice tangent. Outer rim. We have to change the radius now. We have to go from 90 to 0 because we're cutting on the rear quadrant of the part. Let's do the same step over, 0.2 millimeters, same tool diameter, and let's go. And now it's 80 points to move because the radius is larger and it's a larger distance to move. Okay, I tried to visualize here the difference between a small tool and a large tool in relationship to the cusping. Cusping is what sticks out from the nominal surface after you stepped over a radius tool or with the tool radius. This works similar with a turning tool on a lathe, just that it's a thread-like surface then. But you still get this cusping. And this also translates into the surface roughness, depending on how you measure it. But that's a real can of worms that I'm absolutely not going to get into. All you need to know for now is that the larger tool with the same step over than the smaller tool will leave shallower cusps. It's kind of obvious when you see it drawn out like this. So, circling back, that means with larger tool you get away with larger step over to get the same surface finish than with a small tool and a smaller step over. Or you can go faster if you use a bigger tool with the same step over, with bigger step over. You know what I mean, I'm pretty sure. You're smart. The problem is you often don't get away with a large radius tool because, for example, you have to approach a wall and the drawing does not permit such a large radius that's left in an inside edge or a corner. So often we have to compromise on the cutter size and step over. So that's that. And this arc, the center line of this arced slot is a radius of, let's say, R10, and we go from 0 degree to, let's say, 80 degrees, this direction. Let's cut this slot. And the slot width, let's say it's 5 millimeters wide, and for simplicity this hole is also diameter 5. So let's quickly change to a 5mm end mill. This is For demo's sake, I only have a 2 flute end mill here, but this will do fine. This is an uncoated carbide end mill, so not ideal. Since this is 12312 tool steel, P20 plus S is the ACES designation, I think. It's a heat-treated tool steel. Comes in at 35-ish Rockwell C, I think. Not really necessary for this demonstration, but I will also drill the pivot hole. We cannot use the radius function here because this can only cut on either side of a radius, not on the center line. So we're using the bolt hole circle function this time. We're going in the XY plane again. Our X center point is 20 minus, and the Y position is 6. Radius is 10. The starting angle should be 180. Here you can change which part of your angle segment you want to use. So now it's 180 to 100 degrees. That's our 80 degrees of slot. And the number of holes, well, that's a little bit, let's see, I would guess that 50 holes will do fine. Okay. To get the cusping, you could either sketch it out in CAD or sketch it out on graph paper in a larger scale. It's often good enough to space out a few holes and you see the cusping there. Or you just, well, eyeball it. And then you hit enter. And then it wants you to move to the first hole. But I just noticed that 10 millimeter radius with this diameter of tool will create a very, very strange radius. So, oh, yeah, because it's in diameter. So change this to 20 and we get a radius of 10 millimeters. So when we now move to 0, we get our first hole. Okay, let's go. Okay, and as easy as that, I cut an arced slot on a manual mill without utilizing a rotary table or an indexer for that purpose. With the slot width, you're of course limited to your cutter diameter if you do only one pass. If you want to have a slot width that, for example, is 4.5 millimeters, you would have to do 2 passes. One on the outer and one on the inner diameter of your slot width. But that's easy enough to figure out if you really need it. I have done this in an emergency repair or modification situation a few times, and I just used an oversized end mill to the screw, like a 5 millimeter end mill for a 4 millimeter screw, and just used a large thick washer to cover up the slot. Also, this is not ideal because this is really, really thick material, and 5mm is already pushing it for plunge milling here. Especially with a two-flute end mill that has a very thin core. Even more especially with a two-flute end mill that's made for aluminium, not steel. But that's all I had at hand. But yeah, that's as you can see, you can do quite funky things with a DRO and some manual processing. But we're not limited to the XY plane. We can also cut, for example, a radius on this edge here. This was cutting a radius in the XC plane. So the cross sections through the radius is in the X direction and the C direction. And I used a ball end mill. Ball end mill is here, of course, the tool to choose. We are a little bit limited with the DRO what tools you can use for what. For this technique is also called keltering. For keltering, the DRO only allows for a full ball end mill. So let's look at the DRO, how this is set up. So again, in the radius function of the DRO, we changed the plane to XC. We moved the X center point of the radius into the material in the X direction and down into the material in C direction. We're cutting a 5mm radius, so I had to drop it by 5mm. And additional, I had to drop it by the radius of the tool. That's just a quirk of the control or of the DRO. The C center point needs to be in addition with the radius of the tool. Then radius, again, added my 50 safety microns here. And I set it so it starts low down and cuts upwards. I do that to use the side of the end mill, especially with ball end mill. So the side of the end mill cuts it, not the center of the ball, which only has 0. Which the more you go to the center of ball end mill, the lower gets your surface speed, and it goes to 0 when you hit right the center. Step over again 0.2mm, tooling diameter 6mm, and here it is. And then you just step your radius like this. Let's quit. Okay, so these functions are really, really powerful when you want to make a one-off part and just need to add one little radius or one radius groove. You can use this technique also. Well, let's start at 0 and go to -180. You can also use this to cut a radius groove, like a cove, into a part that you don't have a ball or a ball end mill or a form cutter with it. For example, if you want to have a 7.2mm radius here, of course you have to adjust your C drop down here. But that way you have a lot of options. It's really powerful. Okay, let's have a look at this part. The arced slot didn't cut through all the way because the end mill was a little bit on the short side. But ignoring that, we still got a very nice arced slot. just not all the way through. Especially look at the radius here that was done with the ball end mill. This is really a decent finish, considering the fairly, well, 0.2 millimeter step over. It's not too shabby. Same for the small radius here. This is really looking quite nicely. This one, the larger 10 millimeter radius, has one gouge here where I mixed up the axis direction to hand crank. That's one drawback of this technique. If you crank in the wrong direction, you will see it in the finished result very much. But let's put in 5 minutes of handwork, file work, clean it up a little bit. This will tell us once it's cleaned up. Using a flat file here and a piece of 400 grit emery cloth. And this is very much toolmaker or machinist behavior, just doing this with some emery cloth around the file. Here you can see a little bit of blue left. That's where the gouge from my wrong hand cranking is left, but it should clean up quite quickly. Normally with a hard file and filing a radius, I say always drop the file back like this. Never try to follow a radius with a hard file directly. The result will not be brilliant. But rolling the file backwards usually gives a nice result. And we already cleaned up the gouge. With the emery cloth, the technique is more like a seesawing. Yeah, I know clamping holders for emery cloth exist. I own one somewhere, but to be honest, this is better. This costs nothing. This is just a flat file that you already have, hopefully, and a piece of emery cloth that's like cheap. And you can extremely quickly switch your emery cloth around, move to an unused spot of the emery cloth, and it's just more convenient. Oh, and by the way, don't do this. The result will be butt ugly. You will wash down every straight surface, and every edge will be washed down and look really, really terrible. So, and with just a tiny bit of work, we got this radius that blends very nicely into the adjacent surfaces here. It's the same with the small one here. And this is me digging out techniques from 100 years ago because I'm stubborn. And I don't want these techniques to die away because at some point might be useful. This is 400 grit emery cloth. Normally I would start out with a little bit coarser grain like 180, but my spool of 180 is empty. My tool crib guy neglected to order a new spool of emery cloth. Okay, here's the final result with 5 or 6 minutes of handwork and talking to the camera. In reality, it would have gone a little bit faster. But as you can see, we got 3 nicely cleaned up radii. This one is a little bit botched because I had this small gouge that I had to work out. But yeah, this is a good technique for quick and dirty features like a radius or in this case an arced slot. So here's a solution to figure out the coordinates to drive the cutter to if you don't have a DRO, or the DRO you have might be an older model that can't do bolt hole or radius functions. Then we just use the power of CAD software and we draw up our contour that we want to trace. It doesn't have to be a single radius. It can be a radius, it can be an angled line, something like that. And we also put in our cutter that we were using. This time it's a diameter 10 millimeter round insert tool because we're doing something on a lathe. That's also why I have a center line drawn here. I'm going to do, this is Fusion 360 by the way, but I'm only using the sketcher to create a two-dimensional problem solving here. We're going to take a 20 millimeter rod and we're going to put a 7 millimeter radius onto its corner using a 10 millimeter round insert. I'm using a relatively large insert because the larger the radius you're using on the cutter, the smaller the cusps will be, the remaining height of material. You could do this with an almost sharp pointed tool, but then you end up with very jagged contour with very sharp edges. With a large button insert like this, the cusps are very mild and will polish out very quickly. And then I have a driven dimension here. This moves the front, this point of my circle. Put in a line to the OD of the circle. It's attached here, and I have a construction line up here stuck together. So if I change this dimension, like 4, 5, you can see that it drives our sketch along this radius. I start here at 0.5, it starts in front here. So that's the first piece of the puzzle. The second thing that I need to do is I need to measure the diameter this point of the insert reaches. So I'm drawing a second construction line from the center of the insert to its circumference, square, and I measure from this point over the diameter of the part. You do that by using dimension, using this and this. You click the point and the center line, and then it creates a diameter relationship. And this is now an over-constrained sketch, so it creates a driven dimension. This dimension cannot be changed no matter how much you click on it. This will always be driven by the actual sketch. So if I change this, my diameter here changes. So this is still a very manual process. So we start at 1, for example, then you write down, or you put this in a spreadsheet, 5.592, move it over a millimeter, 9.266, and we will do, just for fun, we will do it relatively coarse with 0.5 millimeter increment. So we start at 0.5 and we need a diameter of 2.85, and we move to 1 millimeter. We need a diameter of 5.59, 2, it's 9.26, and so on and so on. And I will finish this off camera because this is boring. Turn the piece of aluminium down to 20 millimeters, and the tool in this position, turning the OD, is now calibrated to 20 millimeters. As can be seen here on the DRO. X is the diameter, 20 millimeters. And with the tool on the face of the part, like this, the C position is 0. So that's the same orientation that I used in my sketch in CAD to derive my C positions, or my diameter positions in relationship to the C position. Here are my notes with all the C positions and my diameters that I need to cut to. We could do two approaches now. I could start in here at the maximum C position, plunge in, move, plunge, move, plunge, move, plunge. But at some point this will get an awful lot of material to remove. So I'm not entirely sure if this will be a proper way to do it, but well, let's try it that way. The other method would be to start out here, plunge in, retract the tool, move over, plunge in, retract, move over, plunge in, retract, and so on, according to the positions that we figured out in CAD. So I will start over here, and I will run the spindle very slow because we're plunging with a relatively wide tool. So 60 RPM it is. So okay, let's go. Let's be the human CNC. Let's take the tool out of the way. As you can see, we got our radius here. Let's find a radius gauge. So here is a 7mm radius gauge. 7mm. And well, it's 7mm. Of course we have the cusping left because of the relatively coarse step over. We did a 0.5mm step over, and this leaves, especially on the steeper parts of the radius, quite the cusping. If we did this, if we cared a little bit more, we would use a smaller increment in the steeper parts of the radius. That's what the radius function of the DRO on the mill does. But all in all, I would say this is a viable option to create one or two radius if you don't want to grind a separate radius tool. A little bit polishing, and this would be a marvelous, nice radius. Here you can see that the tangent to the face is not perfect because my step over is so coarse. The technique I showed on the lathe was with a linear step over. That's how I sketched it out in CAD. And as you saw on the real part, we got a pretty ugly end finish here. And I tried to illustrate it here on paper with linear spacing here, and this ring gauge here acts as my tool. As you can see, it leaves quite the chunk of material in front here, but as soon as we get to like 45 to the center of the radius, the cusping gets very small and very manageable. But here in front, it's very, this is ugly. What's better than a linear spacing would be an angular spacing, like this. I drew this out with a 10-degree spacing with the same radius. And suddenly I get a way more even cusping. Well, I get an even cusping. There is no variance here. From 0 to 90 degrees. On this approach, the cusping changes height with every step. And this will be a little bit harder to, to finish, if you need to finish it, than this. This with a very even cusping will clean up like nothing. So this is definitely the better solution. Or you do a progressive spacing. You start with a fine spacing out down here where the radius starts very steep, and the more shallow it gets, the more it approaches 0 degree, you can widen up the spacing. But that's a lot of effort. I think the angular spacing is a better solution here. And CAD makes it very easy to lay that out. Or if you think that computers are dumb, you can do it with sine and cosine. There's a little bit of work to get there. So you sketch out your radius, you sketch out your tool radius, you figure out the diagonal to get your contact point between the radius. Then you need to get your sine and cosine for x and y. That's over here. And you have to subtract the tool radius or add the tool radius depending on what's your 0 points. If you're running off center point of tool or on the lathe, for example, of the face of the insert. That's a little bit of handwork, but you kind of have to figure it out individually if you need this. I think it's good to know how to do it, and if it's nice. This would also be a very good application for a programmable calculator to have simple programs for these approaches set up and just ready to go when you're at the machine. Walking back and forth to a computer kind of slows you down on manual machines, to be honest, at least for me. When I can stay on a machine, I'm way more productive than when I have to walk to a computer. So sometimes doing it on paper or with a calculator instead of a computer is somewhat nice. Feeling like an old school grump here, and those newfangled computers. But yeah, I think it's not the worst idea to have a basic understanding of geometry. So another option apart from radius function or bolt hole circle would be to use the linear hole pattern. This puts holes across a line. This is especially useful if you want to cut an angled surface, either in the XC or in another orientation. So let's say you want to cut a line that's, let's say, 33 millimeters long, and you want to put, let's say, you want a step over of 0.5 millimeters, so you do 66 holes or 66 positions, and you even can put in an angle. So that's where you can create your angled feature. With this, you have to consider your cutter diameter when you define your starting point. CAD will also help you with that. Let's say you want to cut a part that looks like this. We're talking this blue highlighted surface. I'm just leaving these segments here in the sketch because that creates our full square. Could be, for example, our stock size. So to define my toolpaths, I would go in here, add another sketch on top, and I use project. I would project these two, and I would do a offset, like let's say we have a 6 millimeter cutter, then we would do an offset of 3 millimeter, Now when we put in a 6mm cutter on both ends, as you can see, 6mm. This is our start and end point for our line feature when we set the DRO. Let's say this down here is the 0 that we defined in the DRO. And we just put in, we add 2 dimensions. Hello. And also we add the angle, for example 33 degrees in this case. And also we need the length of this line. Let's etch-a-sketch this out. First I will sketch out the actual outside dimension of this of the part. And I'm doing this with the felt pen marker instead of an end mill because I don't want to waste a whole lot of material just for a demo part. And I think doing it on paper will visualize it just as well. So this is the outer dimension of the part that I showed in CAD before. Let's start with the angled surface back here. Of course, the line width or line weight of the felt pen is less than the 6mm of the cutter that we designed for, but we will get to it. So first we need to move in XY to the start position that we figured out in CAD for this line. We move to 0, and I will set the second coordinate system to 0 so that we have 1 to work with and 1 to fall back for our 0. So we move to X 2.5, 2.51 and a little bit, and to Y is 20.8. And we zero out the DRO in this position. This is the point where this line starts. Unfortunately, in the whole pattern, in the linear pattern function, you don't have the option to define a starting point. You have to zero out the DRO. That's why I have a second coordinate system with my real starting coordinates. So we are 0, 0. And we already punched in the numbers. 36.72mm length. 66, well, let's make a little bit less. Let's make 20 holes so we don't drive ourselves completely crazy. 270 degrees minus 33. 33 is the value from CAD. And then take the negative value of it. 270 because it's 3/4 of a circle. And that gave me the correct orientation and the correct starting point. And now we can just browse through the individual points and cut, or in this case, plot out our line. We drew this line. This is the center line of the toolpath. So we move the line over by 3mm, and now we intersect with the outer contour of the part. What we did here, it basically, if you ever ran a CNC mill, this is cutter compensation. This is what G41 and G42 does. It compensates the toolpath for your cutter and creates the toolpath that you need to walk your end mill along your real contour. If you try this once, and you will immediately understand how it works. I'm very sure. I'm sure all of you are way cleverer than I am. This is, you will do fine. If you need it, you will figure it out. I have to give a huge shout out to Alex, an engineer's finding on YouTube. If you have never watched his videos, close this video and walk over to his channel and watch instead his stuff, because he's not only an engineer, but he's also an excellent machinist and a darn good welder. I learned this, I knew about this technique, but I never saw it applied. And Alex uses this a lot in his own projects and also for tool grinding. In the past, I showed a tool grinding project too, where I did a custom threading tool for an Edison thread, where I used a surface grinder with a relatively similar technique. Back at the CAD, down here, we have the radius. We want to cut this too, so we use again the offset function, and we offset it by 3 millimeters. That's the radius of our cutter. And just for fun, we put in the circles which determine the cutter diameter. And as you can see, here is the tangent point again. For programming or putting in the needed information into the DRO, we need the position of the center position of our radius of this arc. It's x minus 20 and it's in y at 10, and we need the center toolpath here, the radius. This is 13. The radius is 10, and that we want to cut, but the toolpath, of course, is corrected by the radius of the tool, hence cutter compensation on a CNC. So we need 13 millimeters. So let's go back to the machine. So x is minus 20, y is 10, the diameter is 26. We need to set it to arc segment, and we start at 180 degrees and we go to 270 degrees. Let's do only 10 holes because I want to keep my sanity. And there are our positions that we can cycle through. There we go. That's our radius EtchASketched. There we go. That's the radius. So I hope I didn't bore you to death with all my different approaches of trying to demonstrate this technique in various situations and solutions. Also, if you don't have a DRO on your milling machine, first of all, that's the most valuable attachment you can get for any machine tool, a DRO. No matter what, DRO makes your life so much easier. But this technique also works, of course, with the dials on the X or on the different axes of the machine. You just have to be ultra careful not to get into trouble by counting your hand wheel turns. But absolutely doable. People have done it before DROs existed, so it can be done. So I hope you got an idea of why I think this technique is so valuable and that it can be applied to pretty much any machine tool. Mill, lathe, as I showed, surface or tool and cutter grinders, especially if they have a DRO, are very powerful tools in combination with this technique. You can skip some wheel dressing, especially when doing carbide with diamond wheel. And sometimes you need to grind a radius, and it's very time consuming, very much effort to dress a concave radius on a diamond wheel. Also, not all shops have the capability of doing that. So doing it the other way around by stepping the radius off incrementally with a wheel that has a little bit of corner radius, that's way easier and way more approachable. So I hope you learned something useful, or just had a giggle at this very obsolete technique. To be honest, I have to laugh myself sometimes when I show something like this. There are shops out there that run some of the best CNC equipment in the world, and then they watch this channel, and I can only imagine what they're thinking. They must think this guy is out of his mind promoting these techniques in 2024, and you're kind of right. But that's me clinging on to all kinds of skills, I think. Despite having a CNC mill here in the shop, that it's quite a productive machine, but I still enjoy the techniques and skills required for manual machining. And also, I like to be profitable with those machines. I'm making a living with these machines, so don't laugh too hard at me. Thank you all for watching, and thanks for the support. I'll be back.